All right. The one last announcement I wanted to make before we start with the real math, and I know you've heard it, but the people not here may not have heard it. Please do the student course evaluations. They're open. They're out there. Take advantage of them. Get them done. We value your input. Okay? So let us know. All right. My mark is that we're in section 4.6, page 157, very top of the page. And we were going back to review or revisit linear first order differential equations. Okay? Now, there's a little bit of a difference here between what we were doing. Those were linear higher order differential equations, but they all had constant coefficients. Back when we did, what was that, chapter 2, the linear first order differential equations, you were allowed, and this is where we started, we saw in section 2.3, we saw that the general solution of a linear first order differential equation of this form, oops, let me get my pen back to black. Okay, got it. A sub 1 of x, y prime, plus a sub 0 of x, y, is equal to some other function of x. Okay? Now, how this differs from what we were just doing in the last section, the one it's only first order, last chapter, that was earlier in this chapter, sorry. Last sections we were doing were linear differential equations of higher order, but all with constant coefficients. This was the first order differential equation with variable coefficients. The A1 is some function of x, A0 is some function of x, and f of x on the right hand side is, of course, a function of x. No y's can be over there. Now, to solve this the way we were doing it, the first thing we did was divide everything on both sides, whether you remember this or not, was A1 of x. Parentheses around the wrong things. Why is it not, the brain not working this morning? What's that? Yes. I was just indicating my brain's absent too. Okay. Now, basically what this gives you is a coefficient of 1. This gives you some other function of x. It's a rational function, but it's just some function. And this gives you some function of x. Okay? Now, so therefore we rewrite this function, and then for some reason they go to Leibniz notation as if that's going to be better. dy. Okay, it'll be fine. I was just trying to do what the book did, so quite often I don't. I found it's a good book, but it seems like they just drown you in minutia and then hit you with something really hard, without. Okay, so we'll call it y prime plus, now we're going to call this p of x, okay? Now in the past, way past, not this course, but earlier courses, p of x was usually indicating a polynomial function. Obviously, this is not necessarily a polynomial function, so don't assume that's what that means. It's not, okay? Times y is equal to some other function, and shame on, oh yeah, okay, sorry about that. I'm sorry. I botched up, I wasn't paying close attention. They called this one g of x, okay, we had been calling those f's. So they could call this one f of x. Yeah. Meaning it's just some other function of x. Okay, once you get it in this form, then that leads to what we did before. Our now, here's the assumptions. This p of x and the f of x need to be continuous on the common interval I, over which you're doing this differential equation. Using the integrating factor method, and this was that, I found one of the stranger things we did. Okay, your integrating factor is, well, let's just start and go. The first thing you do is integrate this p of x. Okay, just out of the blue, you decide to integrate that. Yes. Negate that integral and have that as the exponent of e. Okay? That's what we do, and that's your integrating factor. Okay? What's that? Yeah. Okay. Now, you can, your answer to the problem is then this. Oh boy. No, I'm sorry. They're doing that. I thought, why are they introducing a minus sign now? They're not. Okay. Not yet. No. Yeah. No, it's not. They have it in here, but we'll see. That's our integrating factor, is the integral e to the integral p of x dx. Okay? Now, they're skipping a whole lot of steps, and it says go back to equation 4 in section 2.3 to see those steps. Okay? But you wind up with an answer that's y is equal to C1, okay, and this is where my eyes are going down to, minus integral p of x dx, okay, plus C2, and it's that function, okay, wait, they don't put the C2 in, do they? Oh yeah, this is first order. They only need one C. Sorry about that. Okay. First order. We've been doing so many higher orders, I forgot. Okay. And this is the part, if you go back and see it, I guess it makes sense, but I don't remember it looking this way, because we probably didn't write it this way. Minus the integral p of x dx. And that then is the coefficient of the integral of e to the integral of p of x dx.
I don't quite remember.
F of x dx. Okay. Got all the pieces in there. Okay. Now, this is not quite probably the best way to do it, but remember, this was our integrating factor, and what we did, we multiplied this by this one, and that one. So that's where this comes from. Okay. It comes from multiplied by all the sides. The left-hand side, if you recall, the reason we chose this e to the integral of this was that it made that, yeah, what?
It made the p of x go away, right?
Kinda, yeah. It became the product rule, okay? And you came up with one function there, and that function happened to be, I believe, if I'm not mistaken, that, okay? Of course, when you integrate p of x, it goes away, it's sort of, this is all not solved for them in the most generic form. And that would be your characteristic solution. The first solution, the one for the homogeneous, would then be this, okay? But then, when we did the particular solution, though we weren't calling it, I don't think we called it that at the time, it would be that times the integral that was left, because you had to, this would have been a derivative, remember? This would, when you put this in, that became, multiply this through, that became the derivative of a product. And using the product rule, you got that, you came out with what that would be, and this is basically what that would be. The solution for that, with the constant with it. And then this also would be the part that you put over here, in a sense, to multiply with that. Now, we weren't annihilating, so don't think of it that way, but it sort of was undoing that. So, in a real generic sense, that's what we were doing. Go back and review that section 2.3, and you'll see it, hopefully, and it'll refreshen you a little bit. The foregoing solution has the same form. Foregoing solution. Swear. What is foregoing here? I guess it's, yeah. Okay, the foregoing solution has the same form as that in theorem 416, namely y is equal to yc, the complementary solution, which this first term is, and yp, which is your second term. Okay. In this case, yc is, that first term, they're saying the same thing I did, and is a solution of the associated homogeneous equation, dy dx is equal to p of x, y equals, plus p of x, y equals 0, and then your particular solution is the second term there, which is your e to the minus p of x dx times the integral of e to the integral of p to x dx times f of x dx. Boy, a whole bunch of x's in there. Most of the time, I think a pure mathematician would have wanted to change one of those variables. Okay? Because, in fact, I have an extra parentheses in there. I'm not quite sure why it's there. Okay. That, ooh. There we go. Okay. All right. It just seems to me that you shouldn't have the x in this integral if that's, the x in here probably is different from the x here, and there, stuff. So you probably should have introduced a dummy variable in there, but they didn't. We can live with it because we know it's different operations. All right, so that's the particular solution. Okay. As a means of motivating, and this is what they do at the first of all these new topics, they're motivating you, okay? As a means of motivating a method for solving non-homogeneous linear equations of higher order, we propose to rederive the particular solution, this one, okay, the particular solution by a method known as variation of parameters, okay? So, where do we begin? Suppose that y1 is a known solution of the homogeneous equation, okay? Maybe something that looked a lot like that, okay? So we know that dy1 dx is equal to, plus p of x, y equals 0. There's the homogeneous, that's y1. Oh, I'm sorry, y1, yeah, okay. Okay, y1. You know that, say, y1 is going to work there. It's easily shown, really careful wording there, yes, intuitively obvious that y1 is equal to, if you look up here, y1 would be equal to e to the, no, I put it in the wrong place, right here.
See, now after they give us the solution of the other one, I can buy that.
Yes, exactly.
But if they just up and said, here's an equation, here's the answer for y1 and y. But,
Yeah.
you know,
Exactly. So that is a solution of this one, that y1 is equal to this. Now notice what I did. I sort of left off the c1 there because you don't need it. You can multiply it by a constant, because if that's a solution, a constant times it's going to be a solution too. But just doing that, that is your solution. We got coming here. Oh. Okay, this class ends at 10:45, but I got another one starting right at 11. So I'm through with that one at 12:15.
12:15.
Right.
So I'll come at 12:15.
Okay.
It's about the recommendation.
About what?
The recommendation.
Yeah, I know. I just haven't had a chance to do it yet. Is it due today?
It's due today.
Okay. I'll try to get at 4. Yeah, okay. Yeah, I can get it done by that. I've got another class starting at 3:15, so I've got 3 hours between 12:15 and 3:15.
Yes, sir.
Okay.
I'll just come back and remind you at 12:15.
Okay. Now I'll either be up here or down in my office.
Okay.
Okay. I think I remember. Okay. So that's your y1 is that. That is a solution to it. With the C1 in there, it's called the general solution. But y1 is equal to that is what? Now, variation of parameters consists of finding a particular solution of this. Okay, I have to find the right equation here. No. Particular solution of that. Sorry about that. Okay. Particular solution there. Okay. No. I was right the first time. My eyes went to the wrong thing. Okay. Let's start over. Okay. The particular solution of that, okay, of the form of, and here's what the generic form would be, and they're still using that y1 here. So yp is equal to u1 of x times y1 of x. Okay? Now, in other words, we have here we said y1 is equal to this. That is a solution. And then we said a general solution would be putting the C1 in front of it, a constant. So what we're doing here for our particular solution is not putting C1 in front of it, but putting another function, U1, as the coefficient of that. Okay? Now it happens to be that this one that we did up here, this was our U1, okay, because the particular solution was this, which is the Y1, notice without the C, but with this, so it seems like to me it would have almost been better to put that in front. This is the U1 they're talking about there, okay? So,
I guess the reason they didn't do that is because of the general.
what's that?
I guess they didn't do that because of the general.
Yeah, this would have been messier to look at. Yeah.
Inside or outside?
Exactly. That's it exactly. Which dx is at the end? The bitter end. Okay. All right. So in other words, we replace the parameter C1 by the function U1. Okay. Now, when you substitute that into your function here, okay, and that's what you're evaluating. Take the first derivative of that, product rule, plus p of x times y plus the f of x, sorry, very thing that you had there, and I guess I ought to do it. I'm going to erase some stuff that I hope will not be essential later, like maybe this right here. Okay. All right. So if you put this particular solution in and you're doing the derivative of that particular solution, that would be, how would you do it? Derivative of that. All right. Of this particular solution down here. Product rule, and how would you do that? Okay, u prime of x, y1 of x, plus u of x, u1 of x, y prime of x, y1 prime of x, okay? Plus p of x, y1 equal f of x. Okay. Now, yeah. Okay. Now, the reason we did, okay. Now, I want, if you look, I hope I didn't erase the, oh, right here, dy1 dx, p of x plus p of x y1, okay, that's equal to 0, okay. Now, wait a minute. I left off one thing. Oh, we're plugging in, this should be a yp right here, not y1. I wondered about it when I wrote it. And that yp is actually u1 of x, y1 of x. Okay, sorry about that. Because we were taking the derivative of, we were plugging this in for the y here. Okay? And so that goes in here. So that gave you this part, u1 x, y1 x. Okay, and that's equal to f of x. There's no y over there, so we're not plugging that in. So then we see this is u1 prime of x, y1 of x, plus u1 of x, because there's a u1 here, u1 there, y1 prime of x, plus p of x, y1 prime, y1 of x, okay, equal f of x. Okay. All right. This thing right here, we see is 0 from down there. So, lose that. So what we're left with, yeah, u1 prime of x, y1 of x is equal to f of x. Okay? Now, part that sort of drives me a little bit crazy here is the, no, I guess it's okay. I was going to say they let so many different things be f of x, it seems like, but I guess it's the same thing. Okay.
I think it's only one f of x.
Yeah, that's what I was thinking. It's showing up in different places, but anyway, let's go on from there. Okay, so that's what we're left with. Okay, so that's y1 du1 dx equal f of x. Now, by separating variables and integrating, we find u1. Okay. Here's why they went to Leibniz notation. They're calling this du1 dx y1 of x equal f of x. Okay. Now, what they claim to be doing here, okay, first thing they're going to do is divide both sides by y1 of x. Okay? Okay. Now, that goes to 1 then. Then, they separate variables. Well, what do we mean by that? They get everything that's just u on one side, just x on one side, except for the u, and leave the u by itself. So, yeah, exactly. That's what they're doing. du1 is equal to, goodness gracious, this quick, isn't it? Okay. F of x over y1 of x dx, okay? And then they integrate both of those, and that gives you u1, which is a function of x still, remember? So that's why I say this doesn't quite feel like a separation. This is equal to the integral of f of x over, that's a y, not a g. Okay. Now, so what is this u of x? The y1 of x, remember, was this thing. Okay, remember? That was this thing, which is also that thing. Okay? And then what is your u here? It turns out being the integral of f of x over this. But that make over a minus, flip it up to the top if you get that. So that's where that part came from. Okay? That's your variation of parameters. Okay? So you don't have to go back and redo this every time. Just get a solution, y1, and don't put a c in front of it, but take that y1, divide that into your f, integrate that rational expression, whatever it happens to be, and then that's going to be the u1. Okay? So it's not necessarily going to be, let's not get too far with it, but that's what you, sorry. So, let's go back here. Your yp, I'm going to delete some of those lines I went crazy writing. Okay. The yp is that u1, okay, times your y1, okay? So they write this, the y1 first, just like they did up here. and that is a function of x, but they don't say that. I think they probably should, times the integral of your f of x over y1 of x dx. Okay. Now, this isn't what's happening here, okay? But it might be what is useful to think of, okay? Your YP, your particular solution, almost looks like it's just you're integrating the f of x on the right. Okay, you're not, but it almost looks like these could cancel out. They don't, okay, because this is inside the integral, that's not. But that might be helpful to help you remember how to put these together. Okay, you just got to find that first solution, which usually you do with a homogeneous case anyway. Okay. All right. Now, that was first order linear, linear first order differential equation. Now we're going to move to linear second order. And this is the part that, okay, differential equation. And that's the next slide. Okay. Next, we consider the case of the linear second order equation. Now, again, it's not like the ones we did in the earlier sections here, in that you have an a2 of x, y double prime, now they go back to prime notation, plus a1 of x, y prime, and that's also of x, but they're not writing it down, plus a0 of x, y, which is a function of x as well, and that's equal to this g of x. All right. Now, hopefully you can do the math, okay? Divide everything by a2 of x, okay? And this will leave you just a y double prime plus some new p of x, y prime, which is just whatever that first coefficient was as a function of x, a1 divided by a2. Plus, now they're going to have a q of x times y, where q of x is a0 of x divided by a2 of x. Okay? And this is equal to some new function, f of x, which is g of x divided by a2 of x. Okay. Now, again, I don't know if they say that here. Yes, we suppose that the coefficient functions p of x, q of x, and f of x, in that second equation there, they're calling it equation 6, are all continuous on some common interval I. So, I meant to say this before, but I failed to. Remember, a2 of x is some function of x. Okay? When you're dividing by that, that can't have a 0 anywhere in the interval, because you're now dividing by that. If that had a 0 in that interval, you know, all bets are off, because you just divided by 0 in that interval. So that's what it means, that this p of x being continuous means that this divided by that has not got a 0 in there. This divided by that, there's no 0. So in other words, you just have to make sure this doesn't have a 0 in that interval. And if it doesn't, you can do this. Okay? They have to be continuous there. All right. That's the sort of shorthand, maybe. Now, in this equation, then, we suppose that the coefficient functions, okay, I already said that. As we have already seen in 4.3, that was a fair amount back, there is no difficulty in obtaining the complementary solution. There's no difficulty in obtaining the complementary solution. Y of c is equal to c1, y1x plus c2, y2x. the general solution of the associated homogeneous equation of that's in here. So in other words, set that equal to 0, and that will give you your YC. Okay? The complementary solution. And that YC is going to be some C1 Y1 of X plus C2 Y2 of X. Okay, we just don't know what they are, but that's what the complementary solution is. When you set that left-hand side equal to 0, that's what you get. Okay. Now, as before, we're going to replace this with a U1 of X, Y1 of X, plus U2 of X, Y2 of X. Okay? Now, that's not going to be a new complementary solution. That's going to be some solution Y is going to work for the constant side, the homogeneous side. Okay. That's a particular, okay. We want that then to be your particular solution that makes that work, the f of x work. Okay. Now goes to that, we now ask, can the parameters C1 and C2 and Y complementary be replaced with the functions U1 and U2, variable parameters, so that the Y is equal to U1 X, Y what? This thing I've written here is also the particular solution. Okay? Well, if it were, then you got a bunch of product rules to do, don't you? Y P prime would be, you tell me, U1 prime of X, Y1 of X, U1 of X, Y prime of X, plus, yep, 2 of X, Y2 prime of X, plus U2 prime of X, Y2 of X. Okay. That would be your first derivative. Guess what your second derivative would be? Yoked. Yeah. Second?
Copy the first thing 4 times, right? No, let's see, 1, 2, 3, 4, yeah, 4 times. The first 2. Right? Oh, wait, no, we already got primes in there, so it's
Okay. Say that again. I'm not sure if okay. U1 double prime of X, Y1 of X, plus U1 prime of X, Y1 prime of X, plus U1 prime of X, Y1 prime of X, plus U1 of X, Y1 double prime of X. Whew. Okay, there's the first 2. Okay, yeah.
U double prime 2
plus U2. Okay. Wait. Okay, you're going to do the...
Oh, we did the last 2 swaps.
Oh, okay. All right. Okay, I'll do that one. U double prime of X, Y2 of X, plus U2 prime of X, Y2 prime of X, plus prime of X, y2 prime of x.
Plus e2 of x, y double prime 2 of x. That was only long and tedious.
Okay. Yuck. All right. I think we got just 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 terms is right. But
Don't tell me we got to take a third derivative.
no, not for this problem. The next one maybe. Okay. But notice these two terms are identical, and these two terms are identical. I don't know where my y went. y2 prime of x. It blinked out, I guess, when you did it. So we can shorten this a little bit. This will
The
be,
two inner terms of the
yes, right. u1 double prime of x, y1 of x, plus 2u1 prime, I'm just going to call it y prime,
Yeah.
plus u1 x y double prime okay. Okay. Goodness, this thing keeps blinking out. Plus 2 u2 prime y2 prime plus u2 y2 double prime. I've decided just to shorten it and leave out some of the x's. Okay. Now, am I going to regret that? Okay, let me see if I will. What we're going to do, okay, all right. Okay. I think okay. We know that this y1 that we started with was the y1 and y2 were the ones that produced a 0 because they were your complementary solutions, two of the complementary solutions. So what we need to do is we're putting these together, try to get those pieces similar, okay? Now, yeah, they left off all the of x's, which I probably should have done. Okay. Yeah. Now, I'm trying to see where I wrote it. Okay. Okay. This was equal to y. Okay. And I went on and named it y sub p. Okay. And you see there, and when you set this equal to 0, this is the line I left out. y1 double prime plus p of x y1 prime plus q of x y1 is equal to 0. Okay, that's the thing that was equal to 0. Okay. And I think you can also say, correctly say, that y2 also fits that bill. So just plug in y2's there too. It's also y2 double prime plus p of x, y2 prime plus q of x, y2. That's also equal to 0. Okay. Now, those two we need, but I was rapidly running out of room for them. Okay. Now, what we're going to do is plug this yp, this one, yp double prime, and this yp, and that yp, okay, into the one with f in it, okay? In other words, we're going to put the yp's here, okay, and plug those in. I know, and I'm going to need a lot more room to do that. So I think, I'm certain I can lose this top line, because that's the one we got the thing from. So let's do our very best to crowd as much into that space as we can. All right. Our y double prime is going to be a u1 double prime y1 plus 2u1 prime y1 prime plus u1 y double prime okay, plus u2 double prime y2 plus 2u2 prime y2 prime plus u2 y2 double prime. Yuck. Okay, that's the that's our first term. Right. Plus p of x times, okay, got to get it back, y prime. Now the y prime is shorter, and I'm going to leave out the of x's here, okay? So this is going to be p of x times, I've got to find it, okay, there it is. In fact, I don't think I want to bracket. I'm sorry, I wish I could, but I believe I don't want to. Unfortunately, I'm going to have to write these in. Okay. P of x, okay, here we have u1 prime y1 plus p of x. Probably don't need the of x there either, but already started. Where is it? There it is. u1 y prime, y1 prime. If I could get it right there. Okay. Plus p, I'm going to leave off the x's now because I'm running out of room. u2 prime y2 plus p u2 y2 prime. Huh?
You're distributing the p's out from one each.
Yeah. And there's a reason for the madness, I hope. Okay. Plus q, I'm not going to call it q of x just so I can save some room here, times your yp, which is just u1 y1 plus Q times U2 Y2. And this is equal to alpha of X. Yuck. Maybe I should just say alpha, but anyway. Now, this is where that next line comes into play. Y1 double prime. This one right here. Okay? If you join that with P Y1 prime, which would be that one, okay, and join that with Q Y1, which is going to be this one, okay, get those together. I think I can lose this line. I hate to lose it because it's sort of a fundamental one. See, if this were the old integrity, I'd just circle it and drag it to the bottom, but I can't do that in this. So maybe what I should do is write it at the bottom. Okay. Y P double prime plus P Y prime P plus Q Y P equal alpha of X. Okay. Okay. So that line I can delete up here. Erase up here.
Probably even get rid of that next one, saying they're all equal to 0.
Yeah, well, the only reason I'm wanting to hang on to it is that's what I'm using right now. So I think I'll write that at the bottom too. Y1 double prime plus P Y1 prime plus Q Y1 is equal to 0, and that's also Y2 double prime plus P Y2 prime plus Q Y2. Okay, that's also equal to 0. So I will erase it up here. Ah, it didn't erase. There we go. I'm getting more than I wanted to erase because it's not erasing. Okay, I erased more than I wanted to. Let me see if I can catch it back. Oh, that's just that. I didn't need anyway. Okay. All right. Now, what's that? Yeah. What I did, these three that I've linked here, this one, and this one, notice all have a U in it, U1 in it. But what they also have in it is a Y1 double prime plus Y1 prime plus Y1, and that from down here, Y1 double prime plus PY1 plus Q Y1, but that's 0. So you can get rid of this term, that term, and that term because the three of them add to 0. Okay. Because of down here. Okay. All right. And similarly, let me change colors. What color you want? Red. Okay. This one, and this one. Okay, notice they each have a U2 in them. And when you pull that out, you have a Y2 double prime plus P Y2 prime plus QY2. That's exactly this down here. So that's equal to 0. Bye-bye, babies. Okay. Those are out of there. All right. Now we get to simplify a little bit. Let's go back to black. And what have we got left? Let me make sure I've done enough. Okay. All right. That leaves me with a U1 double prime Y1 plus 2 U1 prime Y1 prime plus U2 double prime Y2 plus 2 U2 prime Y2 prime plus P U1 prime Y1 plus PU2 prime Y2 equal F of X. Okay. Now, afraid I'm going to have to, let me copy my complementary solution. I don't think I need it anymore, but just in case I do, YC is equal to, no we won't. Yeah, if I need it, I'll come back and get it. Yeah, it didn't erase. Okay, I'll just wipe it out here. We can easily go back and rewrite that one. Okay, and I think it's been pretty patently obvious we've been using that, but let's see what we can go with. Okay, so now if you'll notice, something they did that I probably shouldn't have done. Okay. I wrote these as 2 here and 2 there. They didn't. Okay. So what I'm going to do is undo those again, just for benefit of what we are doing now. I'm sorry. Yeah. That one and that one. I'll come back and write that in a minute. Sorry about this. It's easier for me to do than for you, right? Plus U1 prime Y1 prime plus U2 prime Y2 prime. That's equal to F of X. Okay. Now, what they're noting here is that these two are d by dx of U1 prime Y1. Make sure that's right. Take the derivative of this, you get U2, U1 double prime Y1 plus U1 prime Y1 prime. Yeah. So that's that. These two, d by dx of U2 prime Y2, right? Okay, that's why I had to separate them, because we needed them individually. If you take the derivative of this, you get U2 double prime prime y2 plus u2 prime y2 prime.
Okay, so we're kind of going backwards.
Yeah, we're backing up, reversing ourselves here a little bit, okay? And then I don't think there's much we can do with the p terms there. Just leave them in there. But we might be able to combine plus p, yeah, times u1 prime y1 plus u2 prime y2. I said y2 and wrote u2, okay? And then we have these that we pulled out that we can't do anything with right now. u1 prime y1 prime plus u2 prime y2 prime. That's equal to f of x. Okay. I think we're going to have to lose this one too. If we need it, we'll come back and get it. And I hope that we don't need this y1 prime again. We've used it where we needed it, so we'll get rid of it too. What's that? Yes. You and me both. Okay. Well, it's even worse is the next one, which I'm not going to erase yet, but just because it's going to take too long to erase. Not because I don't want to erase it. Okay. So again, what we're going to do here is get the two of these, separate them a little bit, okay? And they've written them in reverse order, which is okay. Let's combine these two derivatives here. D by dx of y1 u1 prime plus y2 u2 prime. Okay, I didn't need bracket. I could have used parentheses. But you're doing derivative. The derivative of a sum is the sum of the derivatives. So, yeah, that's a legal thing. Okay, in most states anyway. Plus your p u1 prime y1. They probably write this in reversal. Yeah, they do, but I'll do it here. Plus y2 u2 prime plus y1. They probably leave this. Yeah, they don't. Okay. Prime u1 prime plus y2 prime u2 prime equal f of x. Okay, it seems like that's almost a wasted line, but we did it. Okay. These are two unknown functions, u1 and u2. We need two equations. So less I'm sorry?
What's inside the brackets is the same.
Yeah. Yeah. I just have that in reverse. But it's not the same as what's on the outside there. Yeah, okay. Losing where I am in my eye with, following in the eyes. Okay. Now, we need to see two unknown functions, u1 and u2. These are the functions of interest. These are what we're looking for. Whereas before it was your c1, c2, that's u1, u2. Okay, functions now, not constants. Reason dictates, I hate those terms too, we need two equations. Okay, we can obtain these equations by making a further assumption that the functions u1 and u2 okay, why can we say that? Prompted by the first two terms of Okay. It's just like you said, these things right here are the same. And it's sort of like wouldn't it be nice if those were 0? Okay. It seems like you need something better than wouldn't it be nice. But that's just about all you've got here. Okay? Because if those were 0, if I'm sorry.
If we demand.
Yes. y1 u1 prime plus y2 u2 prime. If we set those equal to 0, if that happens to be the case it is, then everything that we've got here simplifies to be this. y1 prime u1 prime plus y2 prime u2 prime equal alpha of x. Okay? If those two were 0, then we're left just with that. And wouldn't that be nice? Okay? So here we have a set of 2 equations and 2 unknowns. Okay? Because what you notice here, the y's and the y, anything to do with y, we're going to sort of count as a coefficient, even though we're starting with the u's as our coefficient. We're going to treat these as if they're something, and we're trying to come down with what the values for u1 and u2 are. Okay? And you'll notice that the u1 and u2 are both primed here and both primed there. Right? Your y1 and y2s, they're different, and the y1 prime and y2 primes are different. But your this other thing. So what they use here, I might as well go on and erase all this. Okay. We've got 2 equations, 2 unknowns. Okay? It's kind of hard to think of them that way, but that's really pretty close to what we got. Okay? Yeah. Yeah. But if that were the case, and that's the case, well then if both of those have to be true, then you got 2 equations, 2 unknowns. So our unknowns here are the u1 prime and the u2 prime, and the sort of like coefficients are your y1s, y2, and y1 prime and y2 prime. Okay? So, and that's basically why they started writing the y1s in front, so they look like coefficients. Okay? So you have 2 equations, 2 unknowns. I'll just copy the second one. y1 prime, u1 prime, plus y2 prime, u2 prime equal alpha of x. Okay. Now, they use Cramer's rule. Okay? Do you remember Cramer's rule determinants? Have you had determinants yet? I know you have in linear algebra, but what's that? Okay, we did have determinants in calculus. I can't remember for sure because I teach all these courses and have for a while. What's that? Okay.
It sounds familiar.
Yeah. Okay. Well, let's. Yeah. Right. Yeah, we certainly did when we were doing. I know what you're talking about. Just can't think of the phrase. The cross products. Yeah, or something like that. Anyway. Well, what we do with that Okay.
Done with this book.
Yeah. I want to refresh you somehow, and I'm not sure this will work, but let me try it.
Well, we're out of time.
We're out of time.
Guess we should probably.
We'll refresh it next time, maybe. Okay. We got
Almost to example.
we got further than I did last time I was doing this. We started at the same place, I think. Maybe not. I don't know. All right, we're starting down here, and we'll do this using Kramer's rule. We'll start right down there. Did we get enough covered? Yeah, I don't think we did do enough to do any new exercises here because we're still trying to build up to it. Unless they had a little, no. These all start with second order.
Is this the whole, they do all this stuff in the beginning and then they hit you with something?
Yeah,
hard?
exactly. And then all of a sudden we'll start doing examples out the ears, you know.
I think,
And this is the last thing we do before we start hitting the examples. So no new homework exercises for you here, but that means you can work on your test, right? And I will try. What's that?
Have you had any turned in yet?
I think that, yeah, I actually turned hers in.
Oh.
Yeah. And she also turned in her paper, by the way.
I turned in my top 3 papers.
Yeah.
I started, okay?
Okay. Good deal. All right,
Two more to do.
we'll close this out. Somehow we still only did